Welcome back to the course entitled Elementary Electrochemistry. In this lecture, we are going to discuss about the determination of dissociation constant of weak acid using the conductance measurements. Dissociation constant of weak acids. We will discuss both weak monobasic acid and then weak dibasic acid like oxalic acid as well. So, suppose the weak acid for us, let us assume it to be acetic acid, is written as HA. A is the anion part of weak acid and H is the H plus ion of that acid. So, weak acid is written as HA when dissolved in water. The following equilibrium is established. HA dissociates into H plus plus A minus. If you assume that alpha is the degree of dissociation, and C is the concentration of the acid, then at equilibrium the individual concentrations of these species will be 1 minus alpha C, whereas concentration of H plus is alpha into C, concentration of A minus is also alpha into C. So, one can easily write the value of dissociation constant Ka as activity of H plus into activity of A minus divided by activity of HA. So, in concentration terms, one can write Ka equal to Ch plus into Fh plus, that is the activity coefficient multiplied by Ca minus into Fa minus divided by Cha into Fha. So, one can further rearrange this expression for Ka as Ch plus into Ca minus divided by Cha into Fh plus into Fa minus divided by Fha, and further one can write Ka equal to Ka prime in terms of concentration. This term is written as Ka prime multiplied by F plus minus square by Fha. Now, for dilute solutions, if HA can be assumed to be equal to 1, therefore Ka can be written as Ka prime into F plus minus square. So now taking log on both sides, log Ka equal to log Ka prime plus 2 log F plus minus. So now one can use Debye-Huckel limiting law and replace this log F plus minus by something called the it is the ionic product. So using Debye-Huckel's limiting law, one can write log F plus minus equal to 0.509 into z plus z minus square root of I, and then for univalent ions, one can write that as log F plus minus is equal to minus 0.509 square root of alpha C. So therefore, one can write log Ka prime, which is this one, equal to log Ka plus 2 into log F plus minus, that turns out to be 1.018 into square root of alpha C. So now if you try to plot the value of log Ka prime multiplied by 10 to the power 5 in y axis and square root of alpha C in x axis multiplied by 10 square, one will get a nearly straight line for a decent range of concentration. So when you extrapolate it to C equal to 0, you will get the value of log Ka prime at C equal to 0, which essentially means that it is the value of log of Ka. So from that one can calculate the value of the activity product of dissociation, or rather the dissociation constant of weak acid using this method. So this plot becomes important. One has to do this experiment, and using various concentration one has to calculate log Ka prime using conductometric method, and from that one can determine the value of Ka. The dissociation constant or constants for a dibasic acid, for example oxalic acid, which is written as H2A can also be determined. This dibasic acid, when dissolved in water, establishes the following reactions or reaction equilibriums. What are those? First, it dissociates from H2A to H plus plus HA minus, that is monodissociated acid ion, and then this HA minus further dissociates as H plus plus A double minus. So, for the first reaction, K1 is written as CH plus into CHA minus divided by CH2A, and the dissociation constant K2 is CH plus CA2 minus divided by CHA minus. So, this is equation A and this is equation B. So, this Ka can be determined like before, right, using the method described for monobasic acid, but then for K2 we need to use a different slightly different method. So, we assume that we have a solution of H2A of concentration C, and it dissociates as follows. H2A dissociates as H plus plus HA minus, equation 1. HA minus further dissociates as H plus plus A double minus, equation 2. Then again H plus combines with HA minus, giving you H2A, equation 3, and 2HA minus also dissociates as H2A plus A double minus, which is equation 4. So, when these four equations are established in a dilute solution of H2A, that is oxalic acid for example, the concentration of acid salt, that is HA minus, and the neutral salt, that is A double minus, are negligible, then we can write that C, the concentration of oxalic acid, is equal to concentration of A double minus plus concentration of HA minus plus concentration of undissociated H2A, which we write equation as C. And also from equation 2 and 4, we can write that Ca double minus is equal to CH plus plus CH2A, which we write as equation D, and CHA minus equal to C plus CH plus minus two Ca double minus, write it as E, is written from C and T. Using equation C and D, we can write this. So now from the equation B, we can write CHA minus is equal to CH plus into Ca double minus divided by K2, which is then equal to C plus CH plus minus 2Ca double minus, or CH plus into Ca double minus is equal to K2 into C plus K2 into CH plus minus 2K2 into Ca double minus. We write this equation as equation number F, right? Now from equations A and B, A and D, we can write CHA minus equal to K1 Ca minus K1 CH plus divided by CH plus as equation G, and then on substitution to equation B, one can get CH plus into Ca double minus divided by K2 is equal to K1 Ca double minus minus K1 CH plus divided by CH plus, or in simplifying, Ca2 minus is equal to K1 K2 CH plus divided by K1 K2 minus CH plus square, which we write as equation number 8, right? So now we substitute this in equation number F, which is here, and then rearranging, one can solve for K2 as K1 plus C plus CH plus into CH plus square divided by K1 into C minus CH plus. Now, when CH plus is small, see, remember that this solution is a very dilute solution and it is a weak dibasic acid, so it dissociates very little. So, at infinite dilution this CH plus is extremely small, so then one can ignore the term here and rewrite K2 as equal to K1 plus C into CH plus divided by K1 into C. So, now by measuring the value of K1 conductometrically and determining the concentration of H plus using potentiometry, one can evaluate K2 using this equation J. Right. So, in a combined method of conductometry and potentiometry, one can determine the dissociation constant of second dissociation constant of dibasic acid. So, I think with this you will be able to solve some of the problems that you may encounter in various textbooks, and one more lecture in which I will try to solve some of these problems which I have given you in one of the previous lectures. Hope you tried to solve those already. So, we will discuss those problems and then we will conclude the course with the experimental demonstrations of conductometric titrations followed by their calculations. So, thank you very much till the next lecture where we will talk about some of the solutions of problems. Thank you.